Welcome to section 7.5, which covers operations with radical expressions. Today, we are going to learn how to simplify radical expressions. We're also going to add, subtract, and multiply radical expressions. The next video will cover dividing. Before we jump in, I want to give a warning right off the bat that this section is tough. So I know the first half of chapter 7 was tough. This is where things really ramp up. And the rest of the section, or the rest of the chapter, is dependent on this video. So it's incredibly important that you do a good job watching this video and listening, and that you understand what you're doing. But again, this is going to be tough. So just know right off the bat, you might struggle a little bit, which is okay. We'll get through this together. So we're going to start with a review, which is simplifying radicals. There are two different methods I've shown you before, and so we're going to review both. For the square root of 20, one method I've shown you is to look for the pairs. So if we break down 20, we can break it down into 2 times 10, and 10 is 2 times 5. We circle a pair of numbers. The pair goes outside the root. The 5 that doesn't have a partner stays underneath the root. So that's my preferred method. I think that's how a lot of you like to simplify your square roots. The other way is to look for perfect squares. So that's what we're going to do with that square root of 96. If you're looking for perfect squares, or you're using that method, you're trying to figure out what is the biggest perfect square that goes into 96. Well, 4 goes in, but we have to think a little bit bigger than that. So 4 goes in, 9 does not go in, 16 does though. So I can think of this like the square root of 16 times the square root of 6. Square root of 16 is 4. Root 6 cannot be simplified. So that's another way. If you like to use that method, you're going to have really good memory of all of those perfect squares. So either method will work, whatever method you are more familiar with. And what we're going to be looking at today is other radicals. So if we look at example 1, it says simplify the following. What if the radical isn't a square root? We can see in part A, this is not a square root. It has a 3 on the outside. This is a cube root. That changes everything. So before we jump into that, let's look at this note at the top. We're going to be looking at nth roots today. So here's some vocabulary for you to know. That number on the outside is called the index. So that 1a has an index of 3. Whatever's underneath the root, we call the radicand. I don't expect you to have those memorized or even to use them really, but you will hear me use those terms. And so you do need to know what number the index is and what number the radicand is. Okay, so square root of, or cube root of 48, how do we do that? It's going to be similar to what we did in part A above. We're going to start by breaking down 48 as much as we can. So 48 is 4 times 12, 4 is 2 times 2, I have 4 times 3, and 2 times 2. Okay, here's where that 3 comes in. We are looking for groups of 3. So in the square root above, we were looking for groups of 2. We're now looking for groups of 3. So I have these 3, which tells me that a 2 goes outside the root. Then I have this 3 and this 2 left over, which go underneath the root. So this is 4, and then root 6. Now what we need to be very careful of is that this is a cube root, like we had in the beginning. So that is our final answer. So whatever the index is always tells us how many we need in a group. So if we look at B, we have the 4th root of 243. So now we're looking for groups of 4. Okay, so I got to figure out what goes into 243. Well, I know that 9 does, and it's 9 times 27. So then I have 3 and 3. This is 9 times 3, and 3 and 3. Okay, 4th root, so I'm looking for 4 at a time. And then I have this 3 left over. Because there's a group of 4, 3 comes outside. This 3 that's left over goes underneath the root. And then we have to remember that index outside to indicate that we have a 4th root left. Okay, so the next logical question, and as you can see underneath in green, is what happens if there's variables? Well, variables underneath the root is going to be a similar idea. So let's look at C. We have the square root of x to the fourth. First thing to know, if there's no index out in front, it's understood to be a 2. It's understood to be a 2. So I'm going to show you a few different ways of approaching these problems. With x to the fourth, what I'm going to do is I'm going to write out what that means. X to the fourth means I have 4 different x's. If I'm looking at a square root, so an index of 2, it means that I need pairs. So I have a pair here, and I have a pair here. 1x comes outside the root from the first pair, 1x from the second pair, nothing's left over. So I get x squared. Okay, in D, we're going to do something similar. This time, we're looking for triplets, or groups of 3, since we have an index of 3. X to the 7, we have 7 x's. So I have a triplet here, I have another triplet here, and I have 1 left over. 1x comes outside the root, another x comes outside the root. That x that's left stays underneath the root. Remember the index. Outside, this becomes x squared and the cube root of x. Now, there is another way to do this that I'm going to teach you a little bit of a faster way. So how else could we have known that x squared was going to come out? Well, your other option is if I take that 7 and I divide it by 3, I get 2 remainder 1. Well, what does that tell us? It tells us that 3 goes into 7 twice. 3 goes into 7 twice, once remaining. So then that x squared is what comes outside. That remainder is what goes underneath the root. Okay, so we're going to approach E using both methods. Nothing's written out in front, so we have an index of 2. If we look at x to the 6th, so we have 6 x's. Index of 2 means we're looking for pairs. So this is x times x times x. That tells us x cubed comes out in front. Nothing left over. Now, y to the 9th. I have 2 different options. I can do that same method and write y 9 times. Or I can do what I did in D with the division. If I opt to do the division, I do 9 divided by 2, and I get 4 remainder 1. So what does that tell me? 2 goes into 9 4 times, once remaining. If I were to circle my pairs, I get 1, 2, 3, 4, remainder 1. So y to the 4th comes out in front. The y that's left stays underneath the root. The y that's left would either be this y or this 1. And then that z is going to come also. Can't be simplified. And that's it. That looks a little funky though, so I'm going to rewrite it. So that's our final answer. Again, what I did with y is I just showed you 2 methods. I don't care which one you use. The division is a little bit more time efficient, but if you want to write out all the y's, you go for it and that'll work for you. Okay, so then last set of examples for this type is when there's numbers and variables underneath the root. So that's what we're going to do next. For F, there's no index, which tells us it should be a 2. We're going to break these all down separately. So if I start with the 32, I get 16 times 2, 4 and 4, 2, 2, 2, 2. Index of 2 means I'm looking for pairs. So I have a pair, 1 left over. So 1 pair comes out, the other pair comes out. The one that's left stays underneath the root. Okay, that x to the 5th. Again, I have 2 different options. I can write out all the x's, or I can do 5 divided by 2. 5 divided by 2 gives me 2, remainder 1. That tells me x squared goes outside. X to the first stays underneath the root. For the y's, same thing. I can write the 7 y's out, or I can do 7 divided by 2, and I get 3 remainder 1. So 2 goes into 7 3 times, but there's 1 remaining. So that y cubed comes outside. The 1 remaining goes underneath the root. If I simplify, I have 4x squared y cubed and the square root of 2xy. Okay, for g, this time I have an index of 3, so we need groups of 3 or triplets. This 27 I'm going to break down. I get 9 times 3 and 3 times 3. Remember, we're looking for groups of 3 at a time, not 2 anymore. That tells me the 3 comes outside the root. There's nothing left over. X to the 10th. Again, we have 2 options. I'm going to show you both on this one. I can write out all the x's. Or I can do 10 divided by 3. 10 divided by 3. Well, 9 divided by 3 is 3, which tells me that 10 divided by 3 is 3 remainder 1. So that tells me I should have x to the third outside and 1x remaining. Don't forget the index of 3. Now, instead, if we like to write out all the x's like I did, you're looking for 3 at a time. So there's how we get our x to the third. There's 3 groups, and then this one remaining. So that is our final answer. Okay, for h, I want you to try h on your own. You try h on your own, please. Pause the video and come back when you're ready. Okay, I'm going to give you the beginnings of the answer so that you can check partially what work you did. We should have 2d e squared f cubed and then the 4th root of 3 and some other stuff left over. So if that's not what you get or got, then something went wrong and you should pause the video and revisit this problem. Okay, let's move on to the next page and keep going. Next thing we need to talk about is operations with radicals, so adding or subtracting radicals. We can see our rules up above. So we have 2 rules. When adding or subtracting radicals, or this is the process really, when adding or subtracting radicals, first thing you are going to do is you are going to simplify each radical. And then you are going to add or subtract the coefficients of like terms. So that raises the question, what is a like term? So like terms for radicals means the radicals have the same index and the same radicand. So we're going to look at some examples so you can see exactly what that means. Example A, we have root 6 add root 6. If I look at my rule, these cannot be simplified anymore. So I'm going to add or subtract the coefficients of like terms. Are these like terms? Do they have the same index? Yes. Index is 2, it's understood to be there. Do they have the same radicand, the same number underneath the root? Yes, they do. What are their coefficients? A 1 and a 1. So this becomes 2 root 6. If I look at B, I can't simplify the square root of 7, so I'm done with step 1. I need to add or subtract now the coefficients of like terms. Are these like terms? Do they have the same index? Yes, 2 and 2. It's understood to be there. Do they have the same radicand? Yes, 7 and 7. So now we need to combine the coefficients. 4 subtract 8 gives me negative 4 root 7. So again, you're adding or subtracting the coefficients, not the number underneath the root. C, similar idea. Can I simplify the radicals? No. I need to add or subtract coefficients of like terms. Here's where we need to be careful. We have a fourth root, and we have a cube root. These cannot be added. These are not like terms. So there's no way, nothing else we can do here. That's the final answer. If we look at D, we notice we have an index of 3 and we have an index of 3, but our radicands are different. So right now, these cannot be added. That does not mean, though, that we are done with the problem, because we still need to simplify each radical. So that's what we're going to do. I'm going to start by breaking 32 down as much as I can. Index of 3 means I'm looking for 3 at a time. So I have these 3, left over, left over. So that means my 2 comes out in front. Those 2's that are left over are going to stay underneath the root and become a 4. Next one, I got to break down 500. So this is 5 times 100. This is 10 times 10. 5 times 2, 5 times 2. Okay, so now I'm looking for groups of 3 or 3 at a time. I have this 5, and that 5. A little funky, so 5 comes out front. I have these 2's that are left over, so those are going to stay underneath the root and become a 4. Ooh, my index is wrong. Okay, I've simplified. Now I need to ask myself, are these like terms? Well, yes, they are. Yes, they are like terms. They both have an index of 3 and a radicand of 4. So adding these coefficients, I get 7 and the cube root of 4. Okay, E is an example for you to try. If we look at rule 1, or the first part of the rule, you are going to need to simplify each radical. So we notice that our radicands are different. Even though the indexes are the same, you're going to need to simplify each radical. So break them down. I will tell you, when you're done, you should end up with an answer of 11 root 3. If you do not have work to back that up, you will not get credit. So please make sure that you show work on this problem. You may want to pause here before going on to example 3. Okay, so moving on, last thing we need to talk about is multiplying radicals. Again, we're going to talk about the rule, and then we will do an example. When multiplying radicals, multiply the coefficients, then the radicands, and then simplify. Okay, one piece to know. The index has to be the same. So that's important to know. We're not going to be multiplying when we have different indexes. Okay, so looking at our example, we have an index of 3. Index of 3, that tells us, yes, it is possible to multiply. So we're going to multiply numbers outside the root. So that gives me an 8. Then the numbers underneath the root. 9 times 6 will give me 54. X cubed, y to the 7th. And now we're going to simplify. We're not finished yet, I'm sorry. So let's break down that 54. I get 9 times 6, 3 times 3, and 3 times 2. Because our index is 3, we're looking for a triplet. So remember, 8 is outside the root. A 3 comes outside the root. This 2 that's left over stays underneath the root. And then I need to simplify that x cubed. Again, I have 3 different options. I'll remind you of both from the beginning of the video. X cubed is x times x times x. If I'm looking for a triplet, I have it right here. So that tells me that x comes outside. Or my other option was to do 3 divided by 3 and I get 1, and that's x to the first. Y to the 7th. I can do my 7 y's. I'm looking for a triplet, so I have 1 here, 1 left over. That tells me y squared comes outside, and that y that's left goes underneath the root. My other option was to do 7 divided by 3. 6 divided by 3 is 2, so 7 divided by 3 is 2, remainder 1. That tells me y squared is outside the root, and that 1 is left underneath the root. Last thing I'm going to do is simplify. 8 times 3 out in front gives 24, xy squared, and then we have the cube root of 2y. Please make sure you do not forget the index. That is by far the most common mistake that I see. Okay, I know that this is tough. Hopefully we paid good attention so that when we come to class tomorrow, we'll have a good idea of what we're doing. If you have any questions, please make sure you write them down. If you're super confused, send me an email, come to office hours, and we can work one-on-one to try to clarify things a little bit. Please make sure that you have this problem from up above done before you turn your notes in, this one. I'll see you in class.